Section 6, functions with discontinuities. All right, so let's start with the definition. The unit step function is defined to be, unit step function, it's defined to be u of t, and it's a piecewise function, right? So it's 0 if t is less than 0, and it's 1 if t is greater than or equal to 0. So that gives us that u of t minus c will still equal 0 if t minus c is less than 0, well, that gives us if t is less than c. And it's still 1, but now instead of just t, you've got t minus c. So if t minus c is greater than or equal to 0, so this is for when t is greater than or equal to c. Okay, so let's write the following. As piecewise functions. And we're going to sketch them too. And sketch. All right, so the first one is if g of t is equal to 2 times u of t minus 3. All right, so let's start with u of t minus 3. So u of t minus 3 will be 0 if t is less than 3, and 1 if t is greater than or equal to 3. But our g of t is 2 times this guy. Well, that will give me that 2 times u of t minus 3. Well, that's just going to be 2 times 0. Well, that's 0 if t is less than 3. And then 2 times 1, which is 2, if t is greater than or equal to 3. So, of course, you don't show the work there. We just multiply it in. And that's how you get it. So you'll just say that it's 0 for t less than 3 and 2 if it's greater than or equal to 3. Let's sketch it also. Just do a quick sketch that it's changing values when t is 3, and we have 0 and 2. And so if it's less than 3, then you're at 0. That's an open dot, and then shading that way. And it's 2 for when t is 3 and greater. So it's just that guy. All right, let's look at second example. What if h of t is t times u of t minus 1? All right, well, let's start with u of t minus 1 will be 0 if t is less than 1, and 1 if t is greater than or equal to 1. So that's going to give me that t times u of t minus 1 will be t times 0 on the first line. So it'll still be 0 if t is less than 1. But now t times 1, so it'll be t now if t is greater than or equal to 1. And what does that sketch look like? So we're changing at 1. So if here's 1, so I should have made it smaller. It's 0 if it's less than, so open dot and 0. And then greater than or equal to 1, it's t. So when it's 1, it would be 1. And then it's got a slope of 1. So it'll just go up like that. That's what the graph looks there. Okay. Next one's a little more complicated. What if f of t is u of t minus 1 minus u of t minus 2 plus u of t minus 3? All right, so what I'm going to do is break it down to each of these parts, right? So u of t minus 1 would be 0 if t is less than 1, and 1 if t is greater than or equal to 1. I'll do And u of t minus 2 will equal 0 if t is less than 2, and 1 if t is greater than or equal to 2. And then u of t minus 3 will be 0 if t is less than 3, but 1 if t is greater than or equal to 3. And so hopefully you can see that things are changing, your values are changing at 1, and then at 2, and at 3, right? So different things are happening in each of these intervals. All right, so I'm going to draw a little number line to just remind me that, for u of t minus 1, it goes from 1 and on, right? And then for 2, if you're less than 2, it's 0, but greater than 2, it's 1, and then it'll change at 3. But what I'm drawing this to help you visualize that for u of t minus 1, when we're at 3, you are definitely greater than 1. Yeah. So hopefully that makes sense. So things are going to be changing from, say, keep in mind this is your f of t, right? So it'll be your f of t will have different parts, right? We're going to have a value for when we'll have if t is less than 1. We'll have if t is greater than or equal to 1, but still less than 2. We're going to have if t is greater than or equal to t is greater than or equal to 2, but still less than 3. And then we'll also have if t is just strictly greater than or equal to 3. So we're going to have 4 parts that are changing here. So when t is less than 1, you've got that u of t minus 1 is 0. You've got minus u of t minus 2. Well, if it's less than 1, then it's still 0. And if it's at u of t minus 3, when it's less than 1, will also be 0. And so the first piece is that your f of t will be 0 if t is less than 1. For in between, so including 1 but not including 2, u of t minus 1, when it's greater than or equal to 1, is 1, minus what's u of t minus 2 when t is strictly less than 2. Well, that's 0. And then when it's between 1 and 2, it's definitely less than 3, so that's a plus 0. And so that piece is equal to 1 when it's between 1 and 2. All right, what about when it's between 2 and 3, including 2 but not including 3? Well, u of t minus 1, if you're between 2 and 3, you're definitely larger than 1. So that piece is 1. And then we're going to subtract from it. What about u of t minus 2? Well, it's greater than or equal to 2, so that's a 1. And then plus, what about u of t minus 3 when it's less than 3? Well, that's 0. So that means when you add 1 minus 1 plus 0, it's still 0. Finally, for when t is greater than or equal to 3, u of t minus 1 will be a 1. You're going to subtract from it u of t minus 2, which is also a 1. If your t is greater than or equal to 3, it's definitely, we're in that section of greater than or equal to 2, right? And then plus t greater than or equal to 3 is 1. So that makes it a 1. So what does this graph look like, right? This piecewise where your f of t is 0 when t is less than 1. All right, so I'll do this. We've got 1 and 2 and 3. And I either need 0 or 1. You know? All right, so when t is strictly less than 1, your f of t is 0. So we got an open dot here and going this way. Between 1 and 2, it's 1, closed dot on the 1, open dot on the 2, horizontal line. Between 2 and 3, I'm at 0, closed dot on the 2, open dot on the 3. connecting those ones. And then when t is greater than or equal to 3, my value is 1. So it's a closed dot there. And then going that way. There's our graph. Okay, let's do one more of this type. That is g of t is t squared times u of t minus 2. So let's start with u of t minus 2. Well, that by definition is 0 if t is strictly less than 2, and 1 if t is greater than or equal to 2, which now means that t squared times u of t minus 2, well, that'll equal t squared times 0, so still 0 if t is less than 2, but t squared times 1 if t is greater than or equal to 2. And what does that graph look like? It's changing at 2. So if here's 2, you've got 0 when it's less than 2, so it's open dot and going that way. And then t squared, oh, I shouldn't have made that so big. Let's pretend like that's 4. Okay, so I've got a 2 squared would be 4. It's a parabola though, so it's like curvy. I don't know. I over-exaggerated the curve because it's kind of more straight looking at that point, but hopefully you get what I'm trying to show you there. Okay. So now what we're going to do is go backwards. Now let's work on, so this was given this unit step function, right? Given the unit step function, no, whatever. Different type. All right, so example 5. We're going to write the following in terms of the unit step function. And we'll sketch it. Okay, so if f of t is 1, if t is less than 1, and t if t is greater than or equal to 1. So they're giving us a piecewise function, right? And now they want us to write it as a unit step function. So it's working opposite, right? The last one they gave us the unit step function, but they wanted us to write it as the piecewise function. Now they give us a piecewise, they wanted us to write it as the unit step function. Okay, so here's how you work this out. What you gotta imagine is, well, let's sketch it first, and maybe that'll help you envision it. It's going to change when t is 1, and if t is less than 1, you've got an open dot there, and it's 1, right? But then when t is greater than or equal to 1, your function is going to be t, so it's a closed dot, same spot, but going up like that. So here's what the graph looks like. So you can imagine that t less than 1, you're going to start off with 1. You're starting off with this value here, right? And then when t is 1, you're going to shut off this function and turn on a new function. Yeah? It's going to switch off. You're going to switch off the first formula and then turn on the second one. All right, so what that means is you start with a 1, start with this function's value right there, right? And then at 1, you're going to turn off the first formula. So that means I need to undo this one. So I'm going to go plus -1 times u of t minus 1, right? And then you're going to turn on the second formula, which means you need to go plus t times the u of t minus 1. Now, let's write that. This was turns off the first formula and then this is turning on the second formula, for lack of a better word. All right, so we subtract the u of t minus 1 to undo this 1, go negative 1, right? And then add the t. So then, but these guys you could combine so that your answer is, you're going to start off with a 1, and then it's a plus a positive t and a negative 1, so t minus 1 times u of t minus 1. That's how you write it in terms of the unit step function, because you're writing it in terms of u. Okay, let's do another one. I'm going to do the same thing, where I'm going to give you this piecewise function. It's equal to cosine of t if t is less than pi, but 0 if t is greater than or equal to pi. So I've given you this piecewise function. Yeah. Let's do a sketch. So cosine, it's going to switch at pi. Cosine of pi is negative 1. So let's go 1, negative 1. It's an open dot, so it'll be there. At pi over 2, you'd be 0, and at 0, you'd be 1. So it, remember, cosine looks like that, right? And then it's 0 for t greater than or equal to pi. So it closed out there and then going that way. All right, so there's the sketch, right, of this piecewise function. Now to write it as the unit function, keep in mind that you're switching off at pi, right? So that means our unit step function will need to be t minus pi, which means that it's 0 if t is less than pi, and 1 if t is greater than or equal to pi, right? So that's what we're basing this off of. All right, but you're starting with a cosine of t. You're not starting with 0. So that means you've got to start off with cosine of t, because that's your starting point. But then, and it'll be that until you get to pi, right? And once you get at pi, now you're at 1. But you got to undo this cosine. So I'm going to multiply negative cosine of t times u of t minus pi. Hopefully by seeing that helps, right? So you start off with a cosine, you need to undo it, undo this cosine so that you end up with, because before it's cosine and then after it's 0 versus this one. Anyway, hopefully that makes sense. You can totally factor out that cosine. Cosine of t, it'll leave you with a 1 minus u of t minus pi. There you go. That's the function written in terms of the unit step function. Okay, let's do another one. How about if h of t is 0 if t is less than 2, 2 if t is greater than or equal to but still less than 4, and then t squared if t is greater than or equal to 4. All right, so let's start with drawing the picture, drawing a little sketch. We need 2, 3, 4, so I'll go small here just because go big on the other one. All right, so there's 2. So when t is less than 2, your h of t is 0. So open and going this way. Between 2 and 4, your h of t is 2. So close dot here, open on 4, connecting a straight line. And then it's t squared for greater than or equal to 4. Ooh, that means I need to go all the way up to 16. So 10 like that's 16. This would be a closed dot, and obviously t squared is a parabola, so it's like curving up and keeps on going like that. All right, so there's your picture of the sketch of this piecewise function. Let's now write it in terms of the unit step function. So I need u of t minus 2, and I also need u of t minus 4, because that's where these guys are changing. That's where the switches are happening, right? So u of t minus 2 is, by definition, 0 if t is less than 2, and 1 if t is greater than or equal to 2. All right. But I need, okay, so I've got 0 here, wonderful, but I have 2 for my y value for when it's greater than 2. So to get the 2 there, that means you need 2 times u of t minus 2, because that'll still give you a 2 times 0 is 0 for when t is less than 2, but it'll now give you a 2 if t is greater than or equal to 2. All right, and then I have the unit step function for t minus 4, right? And that by definition is 0 if t is less than or equal, just strictly less than 4. But 1 if t is greater than or equal to 4. All right, well, I actually have t squared, right, for greater than, so t squared times u of t minus 4, that would give me still a 0 if t is less than 4, but now it'll give me a t squared if t is greater than or equal to 4. All right, and yeah, okay, so what is h of t equal to? Well, we start with 0, so technically it's like a 0 is what we're starting with, and then you're going to turn on this formula. So you're technically turning off this one, but it's times 0, so like I don't even need to put the 0 plus, right? But I did just to be consistent with, you start off with this value. Normally we have to shut that off, but how do you shut off 0? Like, let me go minus 0 times u of t minus 2. You can, but it's times 0, so don't bother, right? But then I need to turn on this function, which we figured out was this guy. So that's a plus 2 times u of t minus 2. So that has turned on this guy. So this switch has been turned off. This one is turned on. We need to go to 4, and then at 4, it's going to switch to this guy. So I need to turn off this function at 4, which means I'm going to go minus 2 times u of t minus 4. And then I've got to turn on the last one, which is t squared times u of t minus 4. Yeah. If it helps, like if you figured what this is, if this part confused you, you know, you need to turn off 2, right? And turn it into a t squared. And so if you figure out what negative 2 times u of t minus 4 would be, it would be a 0 and then a negative 2, and then negative 2 would turn off the positive 2, if that makes sense. Hopefully that makes sense. Okay. Yeah, and you need to turn it off at when it's 4. Turn it on when it's 2, turn it off when it's 4. Okay, so we can clean this up a little bit. We can combine these two guys anyway. So this ends up being that h of t is 2 times the u of t minus 2, and then combining these guys together would be a plus maybe t squared minus 2 times u of t minus 4. Boy, maybe I should do, what if I do brackets on these to make it less confusing? Between this is a function times the unit function. So this is not u times t of 4, this is u of t of 4, versus this is times that. The 2 is not as confusing. All right, hopefully that makes sense. Okay. Let's do one more of these, and then hopefully that'll help it make sense. f of t is equal to 2 if t is less than 1, 3t if t is greater than or equal to 1 but still less than 2, and then 5 if t is greater than or equal to 2. Okay, so let's do the sketch. 5 up to 6. Okay, so 1, 2, 3, whoops, 4, 5, 6. I didn't space those out very nicely, but whatever. Okay, and then it's changing at 1 and at 2. All right, so it's f of t is 2 if t is less than 1. It's 3t if it's between 1 and 2. So if t is 1, then f of t would be 3, and at 2, you're 6. And that is a straight line. 3t is a straight line, so it's just a diagonal line like that. And then it's 5 if it's greater than or equal to 2. Ooh, what did I do? I need an opened up on this guy. Open, closed. I over-exaggerated it, but whatever. Okay, 1, 2, 3, 4, 5. Closed dot and horizontal line that way. So there's the way the graph looks like of this piecewise function. And so how we do this is you'll go f of t is equal to, you're starting off with t, right? F of t is 2, so you're starting with 2. And then you need to shut off the 2 when t is 1, right? Because that's where it's changing. So I'm going to go plus negative 2 times u of t minus 1. Then what gets turned on is a plus 3t times u of t minus 2, minus 1 is what I meant to say. It gets turned on at 1. Yeah. But then the 3t gets turned off when t is 2, so we need to go plus a negative 3t times u of t minus 2. And then 5 gets turned on, so plus 5 times u of t minus 2. So that this piecewise function in terms of the unit step function will be at 2 plus, let's pull together these two guys, the t minus 1s. You'd have a 3t minus 2, or we could put it in order, that's fine. Negative 2 plus 3t times the u of t minus 1. And then for tu of t minus 2, you've got a negative 3t and then a plus 5. So I'm going to use hard brackets again, so that way you can distinguish between, it's this guy times u of t minus 2. Yes? Okay. It's a good time to take a break if you need a break, because we're not close to finishing. Maybe I should have broken this video up into 2 pieces, but oh well, I'm on a roll. You guys can just split up watching it, right? Okay, let's talk about a property. We have a property that says the Laplace transform of f of t minus c times u of t minus c is equal to e to the negative cs times big F of s. Yeah? Okay. This is very similar to property E from section 9.3, but it was like L of Q of T was equal to this. So that means like this is your Q of T. Keep in mind that you've normally, when you've got the when you have the Laplace transform of f of t, then this was big F of s. But now you've got the Laplace transform of little f of t minus c. But this is the Laplace transform on little f of t. Keep that in mind. So what does that mean? That means that that really what we're going to end up doing is this will end up being e to the negative cs times the Laplace transform of f of technically this is going to be little f of t, but your function will have been given to you as f of t minus c. So to undo that, it'll be t plus c. So keep that in mind. You got to figure, like, the function they give you and these guys, because of the shift here, you got to shift it back. That makes sense. All right, so let's practice some, and then hopefully it'll make sense to you. Okay, we're going to find the Laplace transform of e to the t minus 2 times u of t minus 2. So you see, right, you got the u of t minus 2, and this is e to the t minus 2, right? So what they gave you here was t minus c, just like this one is. So what does that mean? You need f of t plus c to figure out what this capital F is. So f of t plus c, which would be t plus 2, will be e to the t plus 2 minus 2, which is e to the t. So that means your big F of s will be 1 over, remember it's 1 right here, so s minus 1. Yeah, so that means that this Laplace transform is equal to, should have left room up there. All right, so that means that it's equal to e to the negative cs, well, your c is 2, so it's a negative 2s times big F of s, which is 1 over s minus 1. There's your answer. All right, let's try that again. How about the Laplace transform on 2 times u of t minus 5? Okay, so 2 is your f of t minus c, and it would be t minus 5, right? So f of t plus 5, it's a constant function, so it's still 2. So that means your big F of s will be 2 over s. Do you remember when it was just a constant? It was the constant over s. All right, so then that means that this guy will equal e to the negative, c is 5s, times 2 over s. All right. How about the Laplace transform on t times u of t minus 3? All right, well, this is t is your f of t minus c, yeah? Which means f of t, well, t is f of t minus 3. So f of t plus 3 will be t plus 3. Yeah? And so the Laplace transform, do you remember, of t, so big F of s would be, t would be 1 over s squared, remember that, and then 3 is just 3 over s. So that means that this is equal to e to the negative 3s times 1 over s squared plus 3 over s. Yeah. Okay, how about one more of this type? How about the Laplace transform on e to the negative t times u of t minus 2? All right, so e to the negative t is f of t minus 2, which means for f of t, what we need is f of t plus 2, which would be e to the negative t plus 2. That? No? Well, but this is e to the negative t minus 2, which is e to the negative t times e to the negative 2. Hopefully using just laws of exponents, right? E to the negative 2 is just a constant, right? So this is e to the negative 2 times big F of s, which your little f is e to the negative t, right? So that'll be a 1 over s plus 1. Well, times e to the negative 2. I guess I should have stuck it in front. Sorry. How about I go, I'll cheat and go times e to the negative 2. Remember, that's just a constant. Yeah. All right, so what does that mean? That means that I have e to the negative cs, so 2s, and then times e to the negative 2 times a 1 over s plus 1. Could leave it, but you can actually clean this up because they both have the same base. So this is equivalent to e to the negative 2s minus 2, which is negative 2 times the quantity s plus 1, and then times 1 over s plus 1. Okay, let's go backwards now. Now, we have another property that says that the inverse Laplace transform of e to the negative cs times big F of s is equal to little f of t minus c times u of t minus c. Yeah. All right, so let's do an example where I want you to find the inverse Laplace transform of 6 over s cubed times e to the negative 2s. All right, so obviously you've got an e to the negative 2s, so your c will be 2. So it'll be u times t minus 2. And then, yeah, all right, so, but this guy, this 6 over s cubed is your big F of s, so that is the Laplace transform of something. So little f will be the inverse Laplace transform of 6 over s cubed. Yeah. And if you remember those Laplace transforms that, oh, I did it over here. Recall that the Laplace transform on t to some power was equal to n that power factorial over s to the n plus 1. Right? So you're going to use that. You're going to have that on your cheat sheet, so you know, right? So I've got an s cubed there, which makes my n a 2, which means this is, can I pull out a 2 out of there? Well, yeah, sure. This is the inverse Laplace transform of, I need a 2, because 2 factorial is still 2. So 2 over s cubed, right? That would fit that pattern. But I need it to be a 6. Yeah. So you can just divide by 2. If I need a 2 here, or you could have just factored out a 3. That works too. I was just making it more obvious, right? That I need my pattern of a 2 here, but it's a 6 here, and so it's a 3 that needs to be in front there. And so that means that the inverse Laplace transform of this guy is a 3 times the inverse Laplace transform of 2 over s cubed, which turns out is t squared. All right, so keep in mind that when you're writing this, the inverse Laplace transform of 6 over s cubed e to the negative 2s, it needs to equal little f of t minus 2 times u of t minus 2. That's the pattern of this guy, right? F of t minus 2 and u of t minus 2. So this is f of t. Well, then that means that f of t minus 2 will equal 3 times the quantity t minus 2 squared. Yeah. So that means we've got 3 times t minus 2 squared, and then times u of t minus 2. All right, let's do another one of those. 14. Let's let's do the inverse Laplace transform of s over s squared plus 4 times e to the negative pi s. Okay, so since I have e to the negative pi s, then that means I need f of t minus pi times u of t minus pi. The u of t minus pi will stay the same. It's this guy that we got to find, right? But s over s squared plus 4 is your big F of s. So little f of t will be the inverse Laplace transform of s over s squared plus 4. And of course, you're going to have all of these formulas in front of you, so you can just identify the fact that, oh, the inverse Laplace transform of that would be cosine of, this is, remember, that's a squared, so it's 2t. So if f of t is this, well then f of t minus pi would be cosine of 2 times t minus pi. Yeah? All right, so that means that this is equal to cosine of 2 times t minus pi times u of t minus pi. There's your first Laplace transform of that one. All right. One more of this type. Let's find the inverse Laplace transform of 1 over s squared plus s times e to the negative s. All right, well, it's got an e to the negative s, so that means that it's going to be an f of t, your c is a 1, so t minus 1 times u of t minus 1. U of t minus 1 is going to stay that way because we're writing it in terms of the unit step function. What we got to figure out is what is little f of t minus 1, given that big F of s is equal to this guy. All right, so little f of just t will be the inverse Laplace transform of 1 over s squared plus s. And you should look at that and go, what? None of them have the pattern of s squared plus s. But what you can do is factor out an s, and you'll have s times s plus 1 down there, and that's still not a pattern. And so what you got to do is do partial fraction decal. So 1 over s times s plus 1. So partial fraction decal. All right, I'm going to set placeholders. They're linear factors, so it's just a over s and then b over s plus 1, right? And that'll end up giving you a 1 is equal to a times s plus 1 plus a b times s. And I'm going to go and do math magic, and you'll end up with a is equal to 1 and b is equal to negative 1. You can figure it out on your own. Remember, you plug in a negative 1 into s and solve for b, and you plug a 0 in for s to solve for a. All right, so that means that this guy is equal to the inverse Laplace transform of 1 over s plus negative 1 over s plus 1. Okay, so now what's the inverse Laplace transform of 1 over s? Well, that's just 1. And the inverse Laplace transform of, well, I guess I should put the negative there. So it's a minus, and the inverse Laplace transform of 1 over s plus 1 is e to the, remember it was always a s minus the number, so a negative t there. All right, so that's little f of t. All right, just a little side note there. So we have little f of t is equal to this, which means little f of t minus 1 would be 1 minus e to the negative of t minus 1. So going all the way back up to here, now that the inverse Laplace transform of the 1 over s squared plus s times e to the negative s ends up equaling f of t minus 1. So 1 minus e to the negative 1t minus 1 times u of t minus 1. All right. Let's do one more example, and that is let's solve differential equation using Laplace transforms. All right, so we've got x double prime minus x prime minus 2x is equal to 1 minus 3 times u of t minus 2. And they also give us that x of 0 is 1 and x prime of 0 is negative 2. Okay, so solving this using Laplace transforms means I am going to take the Laplace transform of both sides of this whole equation. Look back in your notes, the Laplace transform of x double prime is s squared times capital X minus s times x of 0 minus x prime of 0. That's all the Laplace transform of x double prime. Then we're going to subtract from it. So how about if I put it? So this was the Laplace transform on x double prime. Okay, then I'm going to subtract from it, and I'll put parentheses, the Laplace transform of x prime, which is s times capital X minus x of 0. So this guy is the Laplace transform on x prime. Now, and then I have minus 2 times the Laplace transform of x, which is capital X. So this was the Laplace transform on x. And then right-hand side, you are going to take the Laplace transform of this. So this is Laplace transform of 1 is 1 over s. And then we just got done doing this. And in fact, if you look back at example 10, yeah? If you look at example 10, we figured out what a constant times the Laplace transform of a constant times the unit function is. And so you end up with a minus 3 over s times e to the negative 2s. Look back at those notes, but that's the Laplace transform of the right-hand side. Okay, well, they gave us some initial conditions to make our life easy. This guy is 1. This guy is negative 2. And that guy is equal to 1. Yeah, so you end up with s squared times capital X. That's a 1 times s, so a minus s, minus negative 2, so a plus 2. Make sure you distribute this minus sign into both of those. So it's a minus s times capital X minus a negative 1. I mean, I know that's a positive 1, but it was a minus 1. So you end up adding 1. And then minus 2 times capital X. And that's equal to 1 over s minus 3 over s times e to the negative 2s. Okay. Now, combine like terms, because your goal is to solve for capital X, right? So then you can undo the Laplace transform. All right, so let's factor out the capital X. And I would have an s squared minus s minus 2. And then I have this right-hand side. I'm going to add this s to both sides, and I'm going to subtract the 2, and I'm going to subtract the 1. So I have 1 over s minus 3 over s e to the negative 2s, and then a plus s and a This is a 3, so a minus 3. That. Okay. Well, this factors. This is s minus 2 times s plus 1. Okay. And then over here, I'm going to leave the e to the minus 3 over s, e to the negative 2s out front. But then these guys I can combine and make it the same common denominator, right? So it's like over 1. So I would need to multiply by s over s. So this is a plus, would be s squared minus 3s plus 1 all over s. Yeah. So I took the 1 over s and I added it to the s minus 3. So in order to do that, I needed to go times s to get this guy. So 1 over s plus s minus 3 adds up to this fraction there. Okay, solving for capital X. I'm now going to divide both sides by the s minus 2 and the s plus 1. So you get capital X is equal to, I'm going to factor out this negative e to the 2s right here. And it'll be a negative 3 over an s times an s minus 2 times an s plus 1. Right, because I'm dividing both sides of the equation by these two factors. So this guy, that's the negative 3 over s. I put the e to the negative 2s in front here, dividing both sides by those guys. And you also need to divide this fraction also. So I'll have a s squared minus 3s plus 1 over s times s minus 2, s plus 1. Yeah? Okay. So obviously, we're going to have to take the inverse Laplace transforms of these guys. But here you've got an e to the negative 2s, which means there was some kind of shift. And then this one is not. All right, so
I found this on the web for run e to the minus 2 as a second shift. Check it out.
Thanks, Siri. Didn't need your help, but okay. So now what you're going to do is do partial fraction decomp to figure out, because what we need to figure out is what the inverse Laplace transform is of this guy. All right, so let's start with the negative 3 over s times s minus 2 times s plus 1, right? And you'll go, these are all linear factors, so they just a over s and b over s plus minus 2. And c over s plus 1, which will give you a negative 3 is equal to a times s minus 2 and s plus 1, plus a b times s plus 1, and then a c times s minus 2. And obviously you plug in a 2 and a negative 1 and a 0 are the values you'll plug into s. You'll end up getting that a is equal to positive 3 halves, b is negative 1 half, and c is negative 1. So that this ends up equaling 3 halves over s plus negative 1 half over s minus 2, and then plus a negative 1 over s plus 1. So that's how that one breaks up. Then do the same thing for this guy here. So s squared minus 3s plus 1 over s times s minus 2 times s plus 1. Again, linear factors in the bottom, so you don't have to worry about the whole as plus b or whatever, right? So it's just a over s, b over s minus 2, and c over s plus 1, so that you end up getting, I'm not even going to write that out, I'm just going to say, you end up getting a is negative 1 half, b is negative 1 over 6, and c is 5 over 3. I know I just skipped that part, but you practice. I'm good at partial fraction decomp. I don't make mistakes, rarely. I say never, never say never, but I know how to do this, right? You guys practice, because don't mess up on that part, right? Okay, so that means that this guy is negative 1 half over s, and a negative 1/6 over s minus 2, and a positive 5/3 over s plus 1. Okay, we are almost done, almost there. I'm going to go back, I'm going to rewrite what my before I started doing this partial fractions, right? Big X was equal to e to the negative 2s times this guy, right? But now I've broken it down so that I can easily find the inverse Laplace transforms of these guys. So 3 over 2 over s plus a negative 1/2 over s minus 2, and then a plus negative 1 over s plus 1. And then it was plus this guy, and that one would become this one now, negative 1/2 over s plus negative 1/6 over s minus 2 and 5/3 over s plus 1. Okay. These inverse Laplace transforms are easy, right? It's just a constant times, well, if it's over s, then it's just the constant. This one will be negative 1/6 times e to the positive 2t. This will be 5/3 times e to the negative t, right? So that one's easy. This guy, this means that there was a shift. The e to the negative 2s means this was a shift, right? Which means, and it's a shift of u of t minus 2, right? So maybe we write that. Okay, so that means I'll leave myself some room because I'm going to do some work here. That means little x will be, for this guy here, it'll be u of t minus 2 times f of t minus 2. Yeah? Okay, so this guy is, if this is big F of s, right? Well, little f of t would be 3/2 times 1, right? So then what's f of t minus 2? Well, it's still a constant, so it's 1. So that means that this will be a 3/2 times 1, so 3/2. Okay. This guy is a negative 1/2 over, right? So little f of t is e to the 2t, but that means f of t minus 2 is e to the 2 times t minus 2. All right, so I got it, and I have a negative 1/2 times it, so it's a minus 1/2 e to the 2 times 2 minus t. All right, this one is a negative 1 and then times, right? So little f of t will be e to the s minus negative 1, so negative t. So that means f of t minus 2 will be e to the negative t minus 2. I want to do that. And we're multiplying by a negative 1. So a negative e to the, e to the negative t minus 2. This minus sign is coming from that negative 1 there. All right, so this was f of t minus 2 times u of t minus 2. All right, and then plus Laplace transforms of these. Well, negative 1/2 over s, that's just 1 over s is 1, right? And then times negative 1/2, so that's a minus 1/2. This would be a minus 1/6 times e to the 2t. And then a plus 5/3 times e to the negative t. Whoo-wee! Was that a doozy or what? Not too bad, but very time consuming, huh? That's it. That is it. This is it. You have finished 250B. What? Yeah, nice. Congrats. Give yourself a pat on the back.